All right, guys, let's talk about 9.5. 9.5, the title is called the dot product, okay? So the dot product of two vectors, vocab, here we go. If vector v is some given a subscript 1 in the I direction plus b subscript 1 in the j direction, and a given vector w is a subscript 2 in the I direction and b subscript 2 in the j direction, v vector dot, okay, w vector is equals to components a1 times component a2 plus component b1 times component b2, okay? And I want you to be very careful that the answer is not a vector, okay? So if we're doing the dot product of two vectors, the answer is not a vector. Keep that in mind. What are some properties of the dot products? It is definitely commutative. Okay, so what you have is the dot product of v dot w is the same thing as w dot v. Okay, it is distributive. So if you have vector u, not a unit vector, just so you have an understanding, dot the sum of vector v and w, it is now vector u dot vector v plus vector u dot vector w. It also has a zero product property. So if I take zero vector and I dot v vector, and there goes that block box, right? It equals to zero vector. Okay, and one thing I want to add on is if I were to do vector v dot vector v or itself, okay, and it's the same thing as if I were to take the magnitude of v and then square it. Okay, angle between the vectors. So if, there goes the magic box, if vector v and vector w are non-zero vectors, and okay, if vector v and vector w are non-zero vectors, let's do a comma. How about that? And not the word and. Comma. The angle, let's call it theta, and restriction for theta again is between 0 degrees and 360 degrees. Or if we are talking about in radians, we can also do between 0 and 2 pi. Okay, so theta is restricted with one positive revolution, and if theta is between, so the angle theta is restriction, one positive revolution, and is between vector v and vector w. Theta is determined by cosine of theta equals the dot product of v and w, all over the magnitude of vector v times the magnitude of vector w. Okay, the reason I can say times on the denominator is because on the denominator, when I find the magnitude, those are constant numbers. And with constant, I can say multiplication. With vector, I have to use the terminology dot product. Next, parallel and orthogonal. Orthogonal is really a fancy word, guys, for perpendicular, okay? Here we go. Parallel, if vector v, okay, and vector w are, the symbol means parallel, okay? They are parallel if there is a non-zero scalar, let's call it alpha, so that vector v is exactly the same as the scalar times vector w. In this case, the angle, let's use theta, between vector v and vector w is either 0 or pi, okay? Or you can say 0, 180 degrees, okay? Next, if the angle theta between two non-zero vectors, let's call it vector v and w again, okay, is pi over 2 or 90 degrees, okay, then vector v and vector w are orthogonal. That means those two are now perpendicular. Well, piggyback on that, okay, kind of subscript here, if the dot product of v and w, it equals to 0. Well, the zero product would say then either v has to be 0 or w has to be 0, right? That's the only way that when you multiply two numbers equals 0, one of it has to be 0. Then, if that's the case, cosine of some angle between these two has to be 0. So cosine is 0 has to be at pi over 2, right? Or 3 pi over 2. So if it's at pi over 2, then we can say that, okay, then we can say that these two are perpendicular or orthogonal, okay? Next subscript of that is 0 vector is orthogonal to every vector. Okay. So just to recap really quickly is that two vectors are parallel if the angle between them is 0 or pi. Two vectors are perpendicular or orthogonal if the angle between them is pi over 2, or in this case 90 degrees. Okay. Now, if the dot product of the two of them equals to 0, then that means those two are definitely orthogonal to one another. Next, writing a vector in terms of its magnitude and direction. This is sort of a review from last time, so there's really nothing new here. So if we have to write a vector, and writing a vector in terms of its magnitude, we are now going to use theta in the I direction plus sine of theta in the j direction. Okay, so this is a review. This one right here is really important, okay? So I want you to really follow along or kind of listen to it first and then write later. Projection of a vector onto another vector. Suppose that vector v and vector w are two non-zero vectors with the same initial point. So I'm just gonna pause right there, do a little sketch so we have kind of an understanding visually of what I'm trying to say. Okay, so let's do vector v here. Okay, let's do vector w this way. It just said as long as in the same starting point, okay? Keep on going. V, vector V, is decomposed into V sub 1, give yourself some space, and V sub 2, okay? Well, how do I get this V sub 1 and V sub 2? Well, I'm going to use two different colors, okay? Decompose meaning I'm breaking that into two pieces, okay? So V equals, okay, decompose means I'm breaking it into two pieces. Let's call this right here V sub 1, V1. And if I take V1 and I add V2, I would definitely have vector V, okay? So how do I decompose and how do I find what V1 is, okay? V1 is vector V regular dot product with vector W all over the magnitude of W squared times, okay, times vector W. That's what V1 is. And V2 is much simpler. I can just take my regular V, subtract V1, okay? So V1 is decomposed into two, V1 and V2, okay? Now, V1 has a special name, okay? So V1, vector V1, is parallel to vector W, okay? And vector V2 is orthogonal to vector W, okay? And V1 has, like I said, a special name. We call vector V1 is the projection of vector V onto vector W, okay? So V1 is really important, okay? In the book, oftentimes it will use two different variables. You know, it can say, oh, find the projection of F into, like, let's say F and H, okay? F onto H. But the mathematics behind it is still the same, okay? So let's check out my drawing to see if the statement is true, okay? This statement right here said, hey, V1 has to be parallel to W. Well, that's really true, right? W is the green. W is the green. And V1 is definitely parallel to the W. Then it went on and say, well, V2, is it perpendicular to W? Sure it is, right? This is 90 degrees right here. So V2 is shooting straight up. And is V1 plus V2 equals to just V? Sure, okay? Because if V2 equals V minus V1, then if I were to do some basic math, right? Oops, this is supposed to be vector. If I were to do some basic math, I can add V1 back to the left-hand side, and that equals to V, okay? So all of that right there is true. Now we are going to use right away all of these definitions. Example 1, find the dot product. Da-da-da. Okay, so I'm giving to you in the bottom here, V, vector V is negative 2i plus 12j. Vector W is positive 2i plus 3j. The dot product, if you remember just a minute ago, is the first component times the first component of V times the first component of W plus the first component on J times the first component on J of W. Okay, so the first component is negative 2 times 2 plus 12 times 3. This is negative 4 plus 36. So the dot product is just a constant here, and that gives me a 32. Okay. Find the angle between V and W. This is when we have to use cosine. No, you may not use tangent inverse anymore. So cosine is the dot product of V and W all over the product of their magnitude. Okay. So the dot product, we found it already at 32. Okay. The magnitude, I need to do it by hand. So here we go. Square root of V So that's going to be negative 2 square plus 12 square times the magnitude of w, which is 2 square plus 3 square. This is now 32 equals 2 square is 4, 12 square is 144, that's 148 times 2 square is 4 plus 9, that's 13, okay. So 148 times 13, let me bust out my calculator. It's going to be 1924. Okay, so that's just basic math. Now this equals to cosine of theta. I need to find theta, so now I need to use cosine inverse. Okay, so it's going to be 32 divided by square root of 1924. Punch in my calculator. My angle comes out to be 43 degrees. And that looks pretty good. So that's my final answer. C, state whether the vectors are parallel or orthogonal. Okay, so to be parallel, remember we talked about this just a minute ago. To be parallel, the angle in between the two of them has to be 0 or pi, or 0 and 180. To be parallel, the angle has to be pi over, to be perpendicular or orthogonal, the angle has to be pi over 2. So this is 43, so it's neither. Okay, so neither. Example 2. Decompose V into vectors. Okay, ooh, we're using the decomposing now. Decompose V into 2 vectors. Let's call it V1 and V2, where V1 is parallel to W and V2 is orthogonal to W. So how do we decompose? How do we find V1? Remember, V1 is the projection of V onto W, okay? And V1 is super important. We're going to need to know how to do V1 all the time, okay? So to find V1, if you go back to our notes up here, we're going to need to do the dot product of V and W, okay? So it says the dot product, of V and W, okay? All over W, the magnitude of W, and square. Once we have that constant, we are now going to multiply to vector W. And how would we get V2? V2 is, I would take vector V, take away V1 once I know what it is. So let's work out what V1 is, okay? The magnitude of, the dot product, of V and W, we found that earlier from the step above, so that kind of saved me some time, okay? So right there, so this, right away, I can just go and write 32 all over. The magnitude of W, we kind of found that earlier as well. We knew that was square root of 13, okay? But I need to square that, so square root of 13, and I need to square that. So, and then whatever W is, I need to, W is 2i, I need to multiply it back, plus 3j. Okay. So on the top, I now have 32. On the bottom, square root and square, that's now just 13. And I need to make this line a little bit shorter. So now I would just multiply to 2 vector I plus 3j. Let's simplify this, okay, so I can get a v subscript 1 in a nicer way. So let's multiply 32 over 3 times 2, it's going to be 64 over 13, okay, 64 over 13 in the I direction, plus 32 times 3 is going to be 96 over 13 in the j direction, and this is your v subscript 1. To get v subscript 2, you would need to take away v1 is negative 2i plus 12j. Take away your v1, which is 64 over 13, I plus 96 over 13j. I'm going to convert everything into common denominator of 13. So this tells me if this is 13 on the bottom, on the top, 13 times negative 2 is now negative 26, okay? And then plus 13 here as well. So when I multiply that by 13, hopefully I will come up with a nice number. So let's see. What is 13? Multiply this, right? 13 times 12. So, I'm sorry, times 13. So 13 times 12, 6, 2, 3, 1. So 156. Okay, so that's 156. So that's 156, and then this is the j direction. So just kind of combine, just kind of find a common denominator first, okay? So, and then drop this down, 64 over 13i plus 96 over 13j. So now I can put the i's and the j's together, okay? So here we go. Keep on going. These two can go together. Okay. So it's going to be a negative and a negative, so that's going to make it a fatter negative. So that's going to be a negative 90 over 13. So negative 90 over 13 in the I direction. And then, let me just erase this so I have more room. And this right here, this two guys right here, remember I'm subtracting. So 156, take away 96, so I have a nice number. And so that's going to be 60, positive 60 over 13, and that's in the j direction. So this right here, class, is what v subscript 2 vector. I need to go back and add vector. So what's v subscript 2 is. Now, so we took one vector v and we decomposed. We broke it into two vectors, okay? So if I take v1 and v2 and add them together, I should get the original v back. Now remember, v1 is what we call the projection of v onto w. So keep that in mind. That thing's going to come back again and again, okay? All right, and I think I'm going to stop right here. I'm going to save the word problems for class time. Have a wonderful night. All right, guys, example 3 says, a wagon with a set of triplets, those are my kids, as occupants, that weighs 120 pounds. 120 pounds is when they were babies, or much, much younger. They are about 70 pounds each now, and they are almost 10 years old. On a hill with a grade of, can you change that to degrees, 20 degrees for me right there? What is the magnitude of the force that is required to keep the wagon from rolling down the hill? So this problem prompted me when I was, when my kids were little, and I had a wagon. It looks like a train, okay, that has that I would kind of roll them around the neighborhood, and I used to live on a hill. So this question is said, okay, how much force do I need when I pull my kids up the hill to keep them from rolling down the hill, right? To keep them safe. So what we need to do is, it sounds easy enough. Would you agree? It's not that much energy. I just need to make sure my kids are safe. So go ahead and use your technology and do some research. If you're not in physics, this is going to be a little bit of challenging. If you are in physics, you may already know how to do this. Go ahead and search what is a force and write down some definition that makes sense to you, okay? So write it somewhere on here to make sense to you. Don't write down a fancy definition that won't help you understand what a force is, okay? All right, so first thing, we're gonna go and draw a picture for our problem here with a wagon. So I used to live on a hill. I no longer live on a hill. Okay, let's talk about the hill, and then this is the ground. And we change that to 20 degrees, so that's 20 degrees right here. And I used to have a wagon that's like in 3, and yes, they do make a 3 wagon. And my triplets will sit in here, and I would roll them around the neighborhood. So that's a picture. Now, this is one key component right here, is that my kids all together are 120 pounds. So that is, okay, so 120 pounds. So we're going to go in and fill some information here. We will give the vector W. Okay, vector W, that's vector W. And vector W is the force that's parallel to the hill. All right, so vector W is the force that's parallel to the hill. Then we will also give this vector right here, let's call it V, vector V. Vector V is the force causing the wagon to roll. Okay, so there's a force that's parallel to the hill, there's a force that's causing the wagon to roll. So let's write that down. How about that? So W vector parallel to the hill, vector V force causing wagon to roll. Okay, a big no-no. So if V is the force causing wagon to roll, would you agree that the opposite of that is the force preventing from rolling? Okay, so the force that's causing it to roll, opposite of that is the force that's keeping it from rolling. Okay, now we have 120 pounds that has to do something. So 120 pounds is the force of gravity. So let's use F. So my kids are 120 pounds. And so we're going to use F. Okay, so that is the force of gravity. And gravity always go downward. So F equals, and that's going downward, so it's a negative 120 in the J direction, okay, because it's going downward. Now, this is the part where I'm going to try to do this two ways. The first way is I'm going to follow this to the T. It says determine the vector projection F onto W. So we're going to find the vector, okay, projection of F onto W. This will need you to recall some definition from earlier. Remember earlier, okay, I gave you a definition of this. V sub 1 equals vector V dot product with vector W all over the magnitude of vector W square times vector W. And this is the projection. This is just the definition that I gave you prior. Projection of V onto W. Okay. Now, if you remember, I also gave you V sub 2. Remember that? Okay. And so V sub 2 was perpendicular to W. And how did we get V sub 2? V sub 2 was when we took V minus V sub 1. Okay, so remember all of this. This is just kind of recalling your memory. Now, this part right here, determine the vector projection F onto W. So that's the same wording, projector of V onto W. Now they just change it F onto W. So what that means is we are going to replace the equation with some variables. So we can say, okay, so vector V is, we have vector F dot product with W. Since we are still using W, we'll keep W, divided by the magnitude of vector W square times vector W. So we're replacing this right here. Let me get a different color. This for that, and replacing the V1 for V. Okay, just kind of taking out some variables and checking some other ones. So this formula right here will give us the projection of F onto W. Okay, so this right here means, I'm spelling out everything for you because this problem is that difficult. Okay, so this means the vector V is the projection of vector F onto vector W. okay? That means vector v, it's parallel to w based on definition, right? And we can also find a perpendicular vector, okay? So again, and earlier when I wrote down this, remember, I didn't write down the v1 was parallel to w. So maybe if I write that, that will make sense with this, okay? So our vector v equals the dot product of f to w all over the magnitude of w squared times the vector w. Okay, so this is the projection of f onto w. That means this vector v is parallel to w. Now, what would a perpendicular vector look like? So we can go and add that on, okay? We can go and say, okay, well, to find the perpendicular vector, we can, you know what, let me get a different color. Let's get blue since I haven't used it. This right here, we can make that. Remember, W is the force against the hill, so we want a perpendicular. That means we want to make it 90 degrees, okay? So if W is the force parallel to the hill, whoa, that kind of jumped really quickly. This right here, that could also be parallel to the hill. That is going the opposite direction of V, so we can call it negative V, just like that. And to be perpendicular to W, we can call it F2, like 90 degrees, okay? So F2 is the blue. There you go. So that's 90 degrees right there. So F2 is the force that's going to be perpendicular to your, okay, W. Now, how do we get F2? If we really want the force that's perpendicular to the hill, because sometimes it will ask you, okay? To get F2, I'm gonna put a star right here. You can take F1, you can take F or F1, since we didn't have right F1 minus V to give us F2. Some of the questions in your homework will ask for perpendicular force, so that will give you there. This one doesn't. Okay, so let's find V. Ready? Let's do the dot product. The dot product requires us to have vector F, which we do, negative 120 in the j direction. It will also requires us to have vector W. Well, vector W, it's over here. W equals, we don't know the radius, so we're just going to use the unit vector, which is cosine, and we know that's 20 degrees, so 20 degrees in the I direction, plus sine of 20 degrees in the j direction, just like that. So let's do the dot product. You ready? Vector V equals 0, which is your A value for F, times cosine of 20 degrees, plus A2, which is, I'm sorry, not A2, that's already A2. Now we're going to do B1, which is negative 120 times sine of 20 degrees. Close that up, all over the square root of vector W, which is, I'm going to invade this space for a second. That's going to be cosine square of 20 degrees plus sine square of 20 degrees, just like that, times vector W, which is back to cosine of 20, not cosine square, my bad, cosine of 20 degrees in the I direction, plus sine of 20 degrees in the j direction, okay? Now, but look at this one. Cosine square of some angle, sorry, I forgot the bubble, 20 degrees plus sine square of some angle. Doesn't that remind you of cosine of alpha plus sine of alpha? And cosine of some angle, any angle, plus sine square of some angle, any angle, isn't it always 1? Whoa, it is always 1. So look, the denominator just kind of disappear. And then 0 times anything is 0. So guys, we're really just back down to negative 120 times sine of 20 degrees. Okay, so we're just now left with this dude right here, and then W vector. So I'm going to copy that down. Okay, well, I'm going to use my calculator and punch in negative 120 times sine of 20 degrees. Make sure your calculator is in degree mode. That gives you negative 41.04, and then cosine of 20 degrees in the I direction plus sine of 20 degrees in the J direction. And guess what? That is vector V. So we can box that up. That vector right there, okay, is going to be parallel to vector W, which is the hill. Okay? Now it says, find the magnitude of the vector. Okay, so the magnitude of your vector V, its absolute value, which is square root of a squared plus the square root plus b squared, so square root of a squared plus b squared. Okay. Now, usually I would, okay, this is the part where, like, if you're gonna sit here and distribute this and then plug in a squared and b squared, don't bother. Remember, this equation right here, it's in polar form. Okay, this is polar form. So if it's in polar form, isn't it where you guys have the magnitude in the front times cosine of alpha in the I direction plus sine of alpha in the J direction? Well, if it's already in the front and that's the magnitude, and all we got to do now is just take an absolute value of a negative 41.04, beautiful. Then that's all we got to do. Okay, so guys, don't distribute just to plug it back into the square root of a squared plus b squared. Just look at the equation, make sure you know that that's in polar form, and in polar form, in the front number is always the magnitude. So an absolute value of negative 41.04, it's just going to be 41.04. Now, make sure we know how to use the correct unit of measurement. So how much force do I need to keep my kids from rolling down the hill and get crushed by the cars? So 41.04 pounds. Force is used in pounds. So pounds of force is needed to keep the wagon from rolling. Okay, so make sure we know how to interpret our answer. So you have two answers. One is the vector projection of F onto W, and one is that 41.04 pounds. Now, could you have done this another way? Yes, you could, and I'm going to show you now in a different way. You can do either one. It doesn't really bother me how you do it. Okay, so you know we have the angle of 20 degrees. Okay, so based on geometry, we know that since this is 90 degrees, this is then 7 degrees right there. So if that's 70 degrees, this is also 70 degrees. Okay, that leaves me this angle is 20 degrees, just like that. So if you guys remember geometry, that's what's happening. So now this is going to take you guys back into just right triangle trig. Okay, we are trying to look for, remember, vector V, right? The magnitude of vector V, because the force causing the wagon to roll is the same exact force of preventing it from rolling. So it doesn't matter which force I'm going to try to find. I can find either one as long as you find the force, which is the absolute value anyway. It doesn't matter which one you find. So I'm going to try to find this right here. Okay, so let's rock and roll. So I'm going to use sine because sine is the opposite, which is what? Negative V, right? Negative vector V. I'm going to use it to find the magnitude. The magnitude is distance. So that's why magnitude is what we're using. So the distance of vector V divided by the hypotenuse. Well, which one's your hypotenuse? Hypotenuse of this triangle, it's vector F. Okay, and again, we are going to find the distance of this right triangle. So sine oh, you know what? Let's try to cross multiply. Is that okay with you? Okay, get rid of the fractions by multiply both sides by magnitude of f. So now magnitude of f times sine of 20 degrees equals magnitude of negative v. Well, we know, what do we know from here? We only know f, would you agree? So how do we find the magnitude of f? The magnitude of f is absolute value of 120 pounds, right? Because remember, it was told to us earlier. Now, if you don't believe me, we can take the f vector I meant, and then do it by hand. Ready? Magnitude of f equals square root of a squared. Well, a squared is not there because there's no I, so 0, plus negative 120 for b squared. Well, guess what? It comes back to 120. So that's why we know. Okay, so that's our magnitude. As you can see, we're going to take a square root of a negative 20. So it's going to come out to be a positive 120 times sine of 20 degrees here equals magnitude of negative vector v. Well, we're going to use our calculator. We're going to punch it in. Actually, why don't you try? Punch that in for me. Can you please tell me what you get? Remember, absolute value of a negative 120 is somehow a positive 120. Did you also get 41.04 pounds? Okay, so you can use right triangle trig, or you can use the projection f onto w. It doesn't matter which form you use, you should always get the same answer. Now, what if in your homework it asks for the perpendicular vector? You can go further and find the perpendicular vector. And remember, the perpendicular vector is f2. Well, if we're looking for f2, then I'm going to use, would you agree? I can technically use cosine because that's adjacent to 20 degrees. So let's try that, okay? I'm out of space, so can I move somewhere that, here we go, to the left here. We are gonna go do it right here, okay? Perpendicular vector. We're going to do the same thing, but using cosine. So cosine 20 degrees equals adjacent, which is f sub 2, divided by hypotenuse. Hypotenuse is f in this case. We're going to cross multiply. So f times, oops, sorry, these are all distances, so I need magnitude. I lied. Okay, so magnitude of f, bracket, times cosine of 20 degrees equals f2. All right. Well, again, the magnitude of f is, by now we know it's 120. So can we just go straight to there? Okay, equals, trying to find the magnitude of f2. Go ahead, enter that in, and then give me an answer. The question didn't ask for perpendicular, students. I'm just going a little bit above and beyond. I'm going to erase this circle. There you go. All right, ready? The perpendicular force to the hill is 112.76 pounds. Okay, so this is the force that's perpendicular to the hill. All right, that's just an extra. The question in here did not ask for that. Hey guys, this is the last example in chapter 9. Yay! Okay, so before we go and complete example 4, let's define two vocabulary or formula really quickly. The first formula is the work done by a constant force F in moving an object from point A to point B. So this is just really moving it horizontally, okay, without any angles at all. So the work, they use W, is, the formula says, I'm going to spell it out, the magnitude of force times your distance. So that's spelling it out for us. So, but in symbol, as you know already, the magnitude of force is the absolute value, times the distance from A to B. Well, distance is also the absolute value from A to B. Now, this again is the formula for the force. Okay, the force is apply along the line of motion, which is horizontal, along the line of motion, which is again horizontal. Okay, this formula is only for horizontal, which is the force that's applying along the line of motion. Now, what if the force is not horizontal? What if the force is not along the line of motion? For example, if we were moving something and we were pushing it upward or downward. So if the constant force is not along the line of motion, but instead it is at an angle, let's call it theta, to the direction of motion, then the work W is the work W done by force in moving an object from, from A to B is work equals the dot product of force to line AB. And again, dot product is not the same as multiplication. This formula is used when theta is not horizontal. This formula up here is used when you are moving an object horizontally. Example 4. Well, there's an extra one right there. Okay, ignore that one. Example 4. The girl in the figure below is pulling a wagon with the force of 50 pounds. This is the force of 50 pounds. How much work is done in moving the wagon 100 feet if the handle makes 30 degrees with the ground? So makes 30 degrees with the ground, the handle makes that, and she's moving 100 feet. So if you look at the drawing, we need to find two things. We need to find the force, and we need to find the distance of AB. Okay, the distance of AB is pretty easy. She's moving at 100 feet, so if we put her, if her starting point is at the origin, we move it 100 feet horizontally, so that's just 100, 100I, so that's not too bad. Now the force is this dude right here. So the force, we know the force has a magnitude of 50 pounds, and it has a degrees of 30. So we are going to put it in polar. Cosine of 30 degrees plus sine, what is up with the spider web again, of 30 degrees in the j direction. So how do we get this force? We go this distance and we add this distance to get your force. Okay, let's compute 30 degrees and cosine and sine. So force equals, maybe I write it too fast so the spider webs come out. Cosine of 30 degrees is about 3 over 2 in the horizontal direction, plus sine of 30 degrees is a half in the vertical direction. We will simplify this out, which is 25 round 3 in the horizontal direction plus 25 in the vertical direction. So we have the force vector, we have the AB vector in essence. Okay, the dot product work equals the dot product
of these two, which is A1 times A2 plus B1 times B2. A1 is going to be 25 rad 3 times A2 is 100 plus B1 is 25, B2 is 0. So this whole second term is gone. So the force done is 25, the work done, I'm sorry, is 2500 rad 3. And yes, you must give me the right unit of measurement, foot pounds. This is the work. Okay, and that is the end of example 4. Actually, this is the end of chapter 9.